Hi, this is John Whitaker for the Probability 1 class, and this is our 19th video lecture. And today we're going to continue with our work about expected values or conditional expectation. And we had ended last time with an example about the conditional expectation of x given y for a discrete random variable. And now we're going to talk about conditional expectations of x given y given continuous random variables. So we'll start off with the definition. So given two continuous random variables, x and y, the conditional expectation of x given y equals to y is denoted by expected value of x given y, I'm going to say equals to y, and defined by expected value of x given y equal y. It's an integral from minus infinity to infinity of x times the conditional probability density function of x given y dx. Okay. Well, let us look at an example. Let's let x and y be continuous random variables with joint PDFs, given by f of x comma 1 is equal to 12 times x if 0 is less than x is less than y sorry, I didn't write down the right thing. 0 is less than y is less than 2x, which is less than 1, and 0 otherwise. And the question is to find the expected value of x given y equal to y. Before I go any further, let us look at the region where the joint PDF is non-zero. So here, the y values run from 0 to 1, and the x values run from 0 to a half. And so we have this rectangle, and then y being equal to 2x is this line, and we want the y value to be smaller than 2x, so if we take a point, let's say we take the point 0.4, 0.1, that's in this bottom region, and it does fit the restriction, so it's over this region that we'll be doing integration. Now, we previously found, we worked with this problem before, we previously found that the conditional probability density function of x given y was equal to, well, it was a piecewise defined function. It was 8x over 1 minus y squared. If we had 0 is less than y is less than 2x is less than 1. And it's 0 otherwise. Okay, that's what we have. And so we'll use that in computing the conditional expectation. Okay. So, for any, or for 0 less than y less than 1, the conditional expectation of x given y equal to y, well, okay, that's going to be equal to the integral. Okay, so let's look at our region of integration. Remember, we found this conditional probability density function, and it again ranges from 1/2, 0 to 1/2, 0 to 1. We're looking here, this region. And so we fix a y, for whatever y we have here. What do the x values run from this y, for any fixed y? They're going to be from this line. So here, we're going to have, it's supposed to be from minus infinity to infinity of x times this conditional PDF, and we integrate with respect to x. But a lot of times, this conditional probability density function is 0. Where it's not 0 is in this triangle. We fix a y within this triangle that x values run from. Okay. Remember, the region here we were describing was 0 is less than y, less than 2x is less than 1. And so here, the x values will run from y over 2 up to 1/2. This will be x. Here, I write down what that's equal to. The conditional PDF, that's 8x over 1 minus y squared. I'm integrating with respect to x. This is equal to, I have a little one here. Now we're from y over 2 to 1/2, 8x squared over 1 minus y squared dx. That's equal to, here you take out the 1 over 1 minus y squared. The antiderivative for 8x squared will be 8 over 3x cubed. We evaluate that from y over 2 to 1/2. When I stick in 1/2, 1/2 times 1/2 times 1/2 is 1/8. That's going to cancel with that 8 there. So I'm going to have 1 over 3 times 1 minus y squared. And then when I stick in for x, y over 2, again, the 2 in the bottom is going to be cubed and would have 8. It's going to cancel with that y there. And so we have minus, it's going to cancel with that 8 there. We're going to have a minus 1 or y cubed over, I think this is 3 times 1 minus y squared. So 1 minus y cubed over 3 times 1 minus y squared is our answer for this conditional expectation. And here we're having restrictions, again, for 0 is less than y is less than 1. What you can see here is, if you recall the previous example, is that the conditional expectation of x given y equal to y, well, that was some kind of answer. It was in terms of y. So some kind of answer in terms of y. And so we'll write that fact up. So this is just a comment. A fact. The expected value of x given y is a random variable that is a function of y. Now, as a definition, if g of x is a function of the random variable x, then the expected value of g of x given y equal to y is equal to, well, it's equal to one of two things. It's either the sum over the x values of g of x times the conditional probability mass function of x given y, and here it's the integral from minus infinity to infinity of g of x times f sub x given y dx. Of course, this is the discrete, this is the continuous cases. So those are our definitions. Let us look at an example where we would use this definition. So here it says, let the joint density function of x and y be given by f of x comma y equal to 1/2 y e to the minus x times y if 0 is less than x, less than infinity, and y is between 0 and 2, and 0 otherwise. And so here we want to find the expected value of e to the x over 2 given y equals to 1. Okay. Well, this is a situation where x and y are continuous random variables. And so here, this is going to be equal to an integral from minus infinity to infinity of e to the x over 2 f sub x comma x given y of x to the 2 dx. And so we need to compute this conditional probability density function. What was its definition? Well, it's equal to the joint evaluated at x2 over the PDF of y evaluated at 2. Now, f sub y of 2, that's going to be equal to, it's an integral of the joint dx, evaluated at 2. Okay, and so here, that PDF of y, because of the way that the joint is defined, we're going to get an integral, so we think of it for y equal to 2, I'm sorry, for y equal to, I made a mistake, it's y equal to 1. Let's come back. I'm very sorry. So here in our work, this should be y equal to 1. Right. 1. Now, when y is equal to 1, the x values can still run from 0 to infinity for where the joint PDF is non-zero, okay? So when we're calculating the PDF of y evaluated at 1, what that's going to be is going to be equal to the integral from 0 to infinity of 1/2 y e to the minus xy. And remember, y is 1, so I'll change these to 1. And then it is dx. And so this ends up being, here you can pull out the 1/2, e to the minus x. To integrate e to the minus x, what we need is we need the derivative of minus x, which is just minus 1. So I'll put a minus here, 1, compensate for a minus 1 here. The antiderivative of this is minus 1/2 e to the minus x. I need to evaluate that from 0 to infinity. When we let x get really, really big, e to huge negative numbers goes to 0. Minus 1/2 makes plus 1/2. And then when we stick in x being equal to 0, we just get 1. So we just get 1/2 here. Great. Thus, the conditional probability density function of x given y equal to 1 would be equal to f of x comma 1. That's going to be 1/2 e to the minus x over 1/2, which is just equal to e to the minus x. And here x runs from 0 to infinity. Now, the expected value of x given y equal to 1 will be equal to the integral of from 0 to infinity of x, then f sub x comma, or x given y, that's e to the minus x, dx. So that's where we are. Except I made a mistake. It's not the expected value of x we're looking for. It's the expected value of e to the x over 2. So this should have been e to the x over 2. Okay, so that's exactly what we have. Okay, this ends up being the integral from 0 to infinity. Here I can add those exponents, and what I'll get is e to the minus x over 2 dx, which we can integrate by rewriting this as 0 to infinity, e to the minus x over 2. We need a minus 1/2 dx, so we need a minus 2 out in front to compensate for that insertion of 1/2. Then we can find the antiderivative for this easily. And that's equal to minus 2, and here it would be e to the minus x over 2, evaluating from 0 to infinity. So I'm just going to get 2 to do this. Okay, I want to look at another example. I want to let x and y be independent Poisson random variables with finite means, so these are its parameters, lambda 1 and lambda 2 respectively. And here it says calculate the conditional expected value of x given that x plus y equals to n. So that's our problem. X and y are independent, but it turns out that x and x plus y are not independent random variables. We're looking for the conditional expectation. So here starts our solution. Note the conditional expectation of x given x plus y equals to n is defined to be the summation over all x values of x, so here it goes on, so it's x running from 0 to infinity, f sub x, here it would be x plus y, and here it would be x n. Okay? Now, this conditional probability mass function of x given x plus y, of x given n, that's the probability that x is equal to little x and x plus y is equal to n. Okay. Over the probability that x plus y is equal to n. Now, this is the same thing as probability of x equaling x and y equaling to n minus little x over the probability that x plus y equals n. Okay, now x and y are independent, so I can break this down into the probability that x is equal to x and times the probability that y equals to n minus x. And the probability that x plus y is equal to n, well, x plus y is going to be Poisson with parameters lambda 1 plus lambda 2. That's something we had talked about before. So here, this answers e to the minus quantity lambda 1 plus lambda 2. I'm writing down the PMF, I should say, for x plus y with it being Poisson. And then be lambda 1 plus lambda 2 raised to the x all over x factorial. Okay? Except it's not x, it's n. N. Okay, that's going to be equal to, well, the probability that x is equal to x using the PMF is going to be e to the minus lambda 1 to the x all over x factorial times probability of y is equal to n minus x is e to the minus lambda sub 2 lambda sub 2 to the n minus x all over the n minus x factorial. And then, because it's being divided by this, I just flip it. So we have times n factorial over e to the minus lambda 1 plus lambda 2, and then times lambda 1 plus lambda 2. That's what we have. Okay, we simplify that. that's going to be equal to first of all, it's going to be n, you have that n factorial over x factorial times n minus x factorial. I didn't write down the factorial over here. I made a mistake. Let me make this correction very quickly. So this should have been factorial. I don't know, maybe I said it right here. But those n factorial over x factorial, n minus x factorial, they can be combined to give you a combination. So namely, that's n choose x. And then we have a lot of cancellation between the e's. And so we're left with lambda sub 1. We rewritten as lambda sub 1 of x over lambda sub 1 plus lambda sub 2 raised to the x. And then I made another mistake over here. I'm sorry. So here at the bottom, when I wrote down lambda sub 1 plus lambda sub 2, that should have been raised to the n. Okay, it should have been raised to the n. So what I'm going to do is take x of those n's and stick them here. Okay? And then we have lambda sub 2 to the n minus x, lambda sub 1 plus lambda sub 2 to the n minus x. And that's exactly what we have. But if we look at that, turns out if you just take lambda sub 1 over lambda sub 1 plus lambda sub 2, and lambda sub 2 over lambda sub 1 plus lambda sub 2, if you added those together, you'd get 1. Forget the powers of x and n minus x. You get 1. So what this is, well, let me rewrite one thing. So it's n choose x, lambda sub 1 over lambda sub 1 plus lambda sub 2 raised to the x times lambda sub 2 over lambda sub 1 plus lambda sub 2 to the n minus x. And as I was saying, you add these two guys together, you get 1. So this is definitely less than or equal to, I'm sorry, this is a number that's between 0 and 1. So to be thought of as a probability, here's 1 minus that probability. That says the conditional probability mass function of x given x plus y for independent Poisson random variables is the PMF of a binomial random variable with parameters. So what would be involved would be n and, or u to direct on the p. The p would be lambda sub 1 over lambda sub 1 plus lambda sub 2, and the n, the number of trials, is n. Okay? That's what we have. So, the expected value of x given x plus y equal to n equals to, it's a sum, as x runs from 0 to infinity, remember, of x. Well, here, that's right, let's say 0 of f of x given y, x given x plus y. X given n. Okay. And so here, this would translate into a sum just over x running from 0 to n, for binomial, of x x, and here we have, this will be n choose x, lambda sub 1 over lambda sub 1 plus lambda sub 2 to the x, and then lambda sub 1, lambda sub 2 over lambda sub 1 plus lambda sub 2 raised to the n minus x, and that's the expected value of the binomial, okay? And so this is equal to n times p in generic form, which is going to be equal to, so I'll put parentheses for generic form, which is going to be equal to n, and then our p is lambda sub 1 over lambda sub 1 plus lambda sub 2. All right, I would like to look at a fact next, that if we have x and y being two continuous random variables with joint PMF f of x comma y, then we're going to look at the conditional. It's a joint PMF, but that should be PDF here. Okay. Then the conditional PDF of x given x plus y equal to t is equal to the joint PDF between x and y of x evaluate x t minus x. Okay, now let's do a proof of this. And so the first thing I want to note is the joint CDF of x and y. X and x plus y is f of x comma t, which is equal to the probability that x is less than or equal to x and x plus y is less than or equal to t. Okay. Now, here I'm going to think of the x and y's, x plus y, in terms of two random variables, u and v. And here I'm going to think of the v as kind of the y here for a second. And work with this. And so here, what we see is if you let we just pick a t here, we have x plus y equal to t is this line. Okay? And then if we have y equal to x, let's say that's here, then the region of integration here to get this probability is this region that I'm highlighting. So I'm replacing u and v with x for x and y. And so this answer is the integral. Okay. So here's the way I'm going to do it. I'm going to do it dv du. And what do the u values run from? Well, the smallest is minus infinity, so that's outside, and the biggest is whatever x is. And what do the v values run from? Well, for any fixed x value, the v values, minus infinity to x is what the u values run from. For any fixed x value, the v values will run from minus infinity up to this line. Well, that line, it's the way we're writing in terms of u and v, that line is going to be t minus u. And then we would have f of, if you will, it would be uv, okay, where that f is the joint PDF of x and y or u and v. Okay? That's what we have. So, if we take the derivatives, partial derivatives with respect to x and then, with t and then x of f of x comma t, that is going to be equal to, remember this was the joint CDF of x and x plus y. So this is going to be equal to x, the PDF of x and x plus y. I made a mistake in the statement. Okay. So let me back up. I'm very sorry. Here I was saying, well, then the joint or the conditional PDF of x given y. It's not that. It's the PDF of x and x plus y. I made a mistake. Make that change. Because that's what we're finding here. Is equal to so in the statement, I made a mistake. Please make that correction. It's just the PDF, it'd be the joint PDF. And that's where we are. Okay. So we're taking this partial derivatives. Well, it'd be the partial derivative with respect to x of the integral from minus infinity to x. Then the partial derivative with respect to t, minus infinity to t minus u. Here is f. This is of x, y. uv, so that's the joint with x and y. It was dv du, what we had written. So I brought in the partials in these fashion, which will be equal to, when we did this, it's really the fundamental theorem of calculus, and so what we get is partial derivative with respect to x of this integral. Okay. This part is going to be nothing more than f evaluated at u, and then t minus u du. And then, when we do this partial, what we're going to end up getting with fundamental theorem of calculus. That's what I should have said, fundamental theorem of calculus. This is going to be equal to f, and this is x, y. Okay, so the joint PDF of x and y. This will be x, and then t minus x. And that's what we said was the answer we get. The next thing I want to do is talk about a fact involving conditional probabilities. And here's what it says. It says the expected value of x is really equal to the expected value of x given y equal to y. Remember, we think of this expected value, the conditional expected value of x given y equal y as a random variable that's a function of y. And so the proof of this is what I want to do next. And we'll start off with the discrete case, so case 1. X and y are discrete. Okay. Then, what I'll look at is that right-hand side, the expected value of the conditional expectation of x given y equals y. Okay. This is a random variable that's a function of y. So this is going to be equal to the sum over all, this is y values, of the expected value of x given y equal to y. And this will be f sub y of y, the PDF of y. And so here, this is equal to, we just replace what the expected value of x given y is by its definition. So it's the sum over all y values. Here I'm going to write, this is the sum over all x values of x times f sub x given y, of x given y, and then times f sub y of y. Okay, and so when we we replace this by what it's equal to, sum x, here this is f of x comma y, f sub y of y, and here we have f sub y of y. And these two quantities will cancel with each other. And so what we end up getting here is a sum over the y's, sum over the x's of x, and here's f of x comma y. And then that is the definition of the expected value of x, but I'll go a little slower here. But that is a formula that gives you the expected value of x. What I'll do is I'll say, well, we switch rows of the summations, x, y, then of x, f of x comma y, which equals to sum, pull out the x's, as they are constant with respect to y. The sum over all y values is the PMF of x, I should say PMF. And that is the expected value of x. And then I'll just make a comment, I won't do it. Probably leave it for a homework for you, but it works very similarly. So similarly, what we can say is case 2, the continuous case, works analogous to the discrete case. Okay, sometimes conditional expectations can be easy to compute, and so let's look at a quick example. We'll call it quits with that. Takes me a little while to write it up. It's a long-winded problem. It says Sam will read either one chapter of his probability book or one chapter of his history book. if the number of misprints in a chapter of his probability book is Poisson distributed. With mean, let's say, I think here it's 2, and if the number of misprints in his history book is Poisson distributed. With mean 5. Then assuming Sam is equally likely to choose either book. Okay. What is the expected value of the number of misprints Sam will run across? Okay. So here, we let x be the number of misprints. Sam runs across. Okay. And then define y, a random variable, to be equal to 1 if he chooses the probability book, and 0 if he chooses the history book. Then the question is really the expected value of x. What do we have? What's that? And so that should be equal to the expected value of x given, it's the expected value of x given y, and that should be equal to the sum of the expected value of x given y equal to y, where y would run from 0 to 1, which is equal to the expected value of x given y equal to 1, given y equal to 0 plus the expected value of x given y equal to 1. Well, look, if they tell you y is 0, that means he chose the history book. And what's the expected value of x in his history book? Well, that means there was just 2 misprints.
I'm sorry, I made a mistake here. This should have times the probability y is equal to y. Okay? That's the f's of y. So I made a mistake. Here, this is times the probability of y equals to y plus the expected value of x given y equal to 1 times the probability of y equals to, here this should have been 0, here y equal to 1. And so our answer now, this quantity is nothing more than the expected value of x given that he chose the history book, which was 5, times the chance that he chose the history book as a half, because it's equally likely he chose the history book or the probability book, and the expected value of x given y to 1, that means the number of misprints you expect him to encounter if he chose the probability book, and that was 2 times 1/2, so we end up getting 7/2. And that's the answer to this problem. Ladies and gentlemen, that's enough for this video lecture. Thank you very much for your time and patience.